Imagine this. Above a sleeping ocean, the stars look calm and still. Yet inside a stream of fresh telescope alerts, one entry refuses to behave. Its path looks too open, its speed too high, and the tiny heartbeat of its light does not match our usual boxes. A nickname starts to swirl through late-night chats. 3I, an interstellar visitor spotted by the Atlas survey. In a quiet office, a group at Harvard circles a whiteboard and asks a plain question: what exactly are we looking at, and how quickly can we find out before the story runs away from the facts? Most objects you hear about in space, planets, asteroids, and comets, are held by the sun's gravity. They loop around and return. An interstellar object is different. It comes from beyond our solar system, on a path so open it will not come back. The first one we saw was 1I, Oumuamua. The second was 2I divided by Borisov. A possible third, often nicknamed 3I divided by Atlas, would write the next line in that short list. Atlas is a survey that scans for small moving points of light. When one of those points moves a little too fast and a little too straight, people pay attention. Why would any scientist, especially at a place like Harvard, feel a twinge of fear about what this new visitor really is? It is not a movie kind of fear. It is the weight of uncertainty that hides inside noisy data and short observing windows. If the object is ordinary, calling it extraordinary would mislead millions. But if it is truly unusual and we shrug it off, we risk missing one of the rarest opportunities in modern astronomy. Scientists fear both mistakes at once: a false alarm that wastes trust, and a missed signal that wastes history. Here are the first checks. No equations needed. 1. The orbit. Plot the path and see whether it draws a wide hyperbolic arc too open to stay. 2. Brightness flicker. As an object rotates, the sunlight it reflects rises and falls. A fast, uneven flicker hints at a strange shape or a tumbling motion. 3. The fuzzy glow, the coma around the object. Comets vent gas when warmed by sunlight. That gas drifts into a faint cloud. No coma can mean rock or gas too weak to see. 4. A tiny push that gravity alone cannot explain, from venting ice or pressure from sunlight. With careful tracking, even that small nudge can be measured. All of these tests are possible, but in the first nights the data are thin, only a handful of images, a short stretch of time, and many possible fits. A tiny error in position grows into a big mistake in trajectory. A background galaxy can fake a coma. A camera artifact can mimic a flicker. So teams compare notes, reprocess the data, and look for independent confirmations separating signal from noise before speculation hardens into certainty. There is another layer to the tension. Interstellar speed is high. Even a small rock from deep space carries enormous energy. No one is losing sleep over a world-ending strike from a single pebble, but a dark object on a steep path will test our ability to track, model, and communicate. It might flash in the upper atmosphere, fizzle in a short trail, or in rare cases punch deeper before it slows. Every rare visitor becomes a stress test of our planetary defense playbook. Memory adds weight. Oumuamua did not act like any comet we expected. No classic tail, a gentle non-gravitational push, hints of odd geometry. Borisov looked like a textbook comet. A third object becomes a tiebreaker. Does it behave like a normal comet from another star, or does it write a new rule again? Every path we measure, every color we record, and every tiny push we detect will help answer that. There is also the human side. When a candidate interstellar visitor shows up, the internet lights up. Headlines sprint ahead of the science. The risk is not only getting the physics wrong, it is letting a confused story harden before the facts catch up. So researchers try to move fast and speak carefully, confirming if it is interstellar, correcting if it is not, before a myth takes root. Here is our plan, calm and clear. First, we will unpack what the telescopes saw in those first hours, and how raw pixels become an orbit on a screen. Then we will look at the fingerprints of a natural comet, and how those differ from an airless rock. After that, we will explore the more exotic ideas that appear when the data refuse to sit still, and why cautious minds treat those ideas with both openness and restraint. Finally, we will ask what 3i, whatever it proves to be, can teach us about other star systems and about our own. For now, picture the scene one more time: a quiet lab. Coffee gone cold, a dozen dots of light blinking on monitors. The room is not afraid of monsters. It is afraid of wasting a once-per-decade chance because the team did not move fast enough or think wide enough. That is the weight behind our title. Why do Harvard scientists fear what 3i divided by Atlas really is? They fear the cost of being wrong in either direction, the story we will tell ourselves if we rush, and the discovery that might slip past if we do not look closely enough. Take a breath, settle in. The journey you are about to hear will be careful, simple, and steady. We will use clear words. We will move at a relaxed pace as the background shows slow, soothing scenes of stars drifting by. We will open a door on a mystery that may be small, may be huge, but is certainly worth our full attention. People imagine discovery as a scientist shouting "Eureka" at a dramatic photo. In truth, the first sign of an interstellar visitor is almost nothing, a faint speck that shifts between two frames. Atlas, the survey that flagged the candidate, nicknamed 3i, lives for that quiet drama. It takes wide, rapid snapshots of the sky and marks anything that moves. Most movers are familiar asteroids, satellites, even camera ghosts. A tiny fraction refuses easy labels. That is where the work begins. The pipeline from spec to story is careful. Software says, "This point moved." A human asks, "Did it really?" Observers compare the motion with star drift, thin cloud, and camera quirks. If the dot still looks real, its coordinates and timestamps go to a clearinghouse so other telescopes can chase it. Those repeat sightings turn a guess into a path. With a few good positions across a night or two, the computer sketches an orbit. With a week of points, the sketch becomes a shape you can test. Think of orbits like paths a ball makes in a bowl. If the bowl is deep, the ball circles and returns. That's a closed, bound path. If the ball arrives fast enough, it skips the lip and never comes back, a one-time pass. In space, the closed path is an ellipse around the sun. The one-time pass is a hyperbola. When early positions fit that open curve, astronomers whisper interstellar, but softly. Early fits can be fooled by bad timing or a warm camera. Caution is not fear of the sky. It is respect for small numbers. So why would Harvard scientists feel a twinge about 3i? Not because they expect monsters or doomsday. They fear a rumor outrunning a result. The cure is simple but hard. Widen the base of the triangle. More data points, more nights, more colors. Color matters because it hints at surface chemistry and dust. Split light with a prism, and you already understand spectroscopy. Each material leaves a tint, a fingerprint. Brightness changes matter too. Hold a potato under a lamp and spin it. Bright, dim, bright, dim. That rhythm is a light curve. Space rocks behave the same. A long, thin body flashes more. A round one hardly flickers. If 3i's light rises and falls by a lot, that suggests a strange shape or a tumble. If it stays smooth, that suggests a compact body or a soft halo smoothing the light. That soft halo has a gentle name, coma. When ice warms in sunlight, it turns to gas and carries dust, making a fuzzy glow around the solid core. A classic comet shows both coma and tail, but the gas can be faint. Early images can miss it, label the object wrong now, and the world points the wrong tools at it. The fear is not the coma itself. It is mislabeling that steals precious nights. There is also a push that is not gravity. Sunlight nudges, venting gas nudges. You would never feel it, but over weeks the path drifts in ways math can trace. If the drift lines up with heating by the sun, a natural explanation gains strength. If the drift is there but the reason is unclear, caution rises. The lesson from Oumuamua still echoes. Ordinary physics can look odd when the object is small, and the data are thin. What about danger? Here, the plain truth soothes. An interstellar visitor arrives fast, yes, but even a fast pebble is still a pebble. Earth's atmosphere is a safety net that catches small bodies every night. They flash and break. Larger bodies are found early and tracked well. Planetary defense teams drill this all year with homegrown asteroids. A 3I object is mostly a test of process, not a reason for panic. The fear is reputational and scientific, getting fooled by noise or ignoring a real signal. Inside any good group, skeptics act as safety devices. One asks, could the flicker be a bad pixel? Another, could a background galaxy fake the halo? A third, check a different telescope, a different filter. The team lines up ordinary explanations before unusual ones. That does not cage curiosity, it protects it. If an exotic idea survives those tests, it earns the right to be explored. If it doesn't, the community keeps its trust. Communication matters too. When a candidate interstellar object appears, conversation runs hot. It is tempting to mint big headlines, but the people measuring the light know the plot can shift each week. So they use steady language. Candidate, not confirmed. Preliminary, not final. Those words are not hedges. They are a promise to let facts lead. Next comes choreography. Big telescopes are busy, so you need a tight plan. What to measure, how long, and why it matters. Small telescopes can keep watch nightly, building a light curve and refining the orbit. Radio dishes may listen for natural molecules, like the signal from water breaking apart. Infrared eyes can look for warm dust. Each method weighs in on the same question: rock or ice, smooth or dusty, bound or unbound. As nights pass, the path settles. The orbit chooses, bound or unbound. The light curve smooths or stays wild. The colors lean toward dusty ice or dark rock. Out of that mix, a result forms you can trust, maybe not perfect, but solid enough to carry forward. And with it, the tone shifts, from careful maybe to confident yes. If the yes is interstellar, a third point joins our short line of visitors, and everything we learn sharpens our sense of how common these travelers are. That is how a dot becomes a diagnosis, not through one dramatic picture, but through patient, layered seeing. Keep that in mind as we move on, because the next chapter asks a bolder question. If the path is open, what can its speed and color tell us about the kind of star system it came from? Think about a passport stamp. One tap on a page tells you where you came from and how quickly you passed the gate. In astronomy, speed and color act like that stamp. When a candidate like 3I Atlas first appears, those two clues, how fast it travels and what shade its light carries, start whispering an origin story. Our job is simple. Read the stamp cleanly while the visitor is still in view. Start with speed because it shouts. Our part of the Milky Way has a traffic flow, like cars cruising the same highway. Homegrown comets and asteroids move with that flow. A true interstellar traveler is like a car merging from a different highway and cutting across our lanes. Even after the sun bends its path, its baseline pace stays high. If repeated measurements show the object keeps that extra speed, and its arc is open never to return, the interstellar case grows stronger. That one clue, measured carefully over several nights, can change maybe into probably faster than any photograph. Now, color, which sounds like cosmetics but is really chemistry. When you split an object's light into a soft rainbow, certain shades brighten or fade. Dust rich in complex carbon often looks redder. Fresh ice can reflect a touch more blue. Years of space weathering darken everything. We do not need a lab bench to learn something useful. A handful of filters like sunglasses that each pass a different color already hints at whether the surface is dusty and old, fresh and icy, or dark and rocky. If 3I turns out to be unusually red while it brightens, that leans toward a cold, dusty surface waking up in sunlight. If it stays gray and steady, that leans toward rock. Put speed and color together, and the map narrows. A fast red object points to the deep cold outskirts of another star system, where ice and dust linger far from heat. A slower, grayer one might be a rocky chip, flicked free from a warmer inner zone. The group at Harvard folds in a third clue: how brightness changes with distance from the sunday. If it brightens faster than simple geometry predicts, sunlight is not only shining, it is stirring gas and dust into a soft halo called a coma. If it brightens only as fast as distance would suggest, the surface may be bare rock with little gas to release. 3 simple threads, speed, color, brightening can knit a surprisingly strong story. Still, the stamp can be smudged. Instruments have small biases. One camera might tilt toward red. Thin clouds can nudge faint objects even redder. A quiet background galaxy can lift the brightness curve without anyone noticing. Each tiny flaw nudges the story. That is why careful teams ask for independent confirmation. When telescopes with different cameras, skies, and filters see the same color trend and the same speed pattern, confidence climbs. When one site's numbers disagree, you hunt the hitch before you harden a claim. This is not fear of being bold. It is the discipline that keeps boldness honest. There is also the matter of gentle pushes. Sunlight does not only illuminate, it nudges like a breeze. If 3i sheds gas as it warms, those tiny jets act like puffs from a miniature rocket, and the path shifts a little. The shift is small, but trackable over weeks. Picture a leaf gliding down a river while a side wind pushes it toward one bank. If the drift grows near the sun and fades far away, you can blame sunlight and venting. If a drift shows up with no clear reason, people pause. The last time we met that kind of puzzle, arguments bloomed about what physics could explain it and what could not. No one here wants to replay that debate with sloppy data. Origins invite daydreams, so let's use them carefully. Suppose 3i came from the cold pantry of another star, a loose shell like our own distant comet cloud. A passing giant planet could have flicked it out, the way a soccer ball glances off a goalie's glove and sails into the stands. Then, we are catching a sample of deep cold chemistry, preserved far from any Sunday. Suppose instead, it is a rocky chip from a warmer inner zone, freed by a near miss with a big planet. That would make it a shard of crust from elsewhere, telling us how rocks form and weather in another system. Neither story needs exotic claims. Both are exciting, both are testable, and both demand neat, patient measurements, while the target is bright enough to study. Timing matters. The closer the visitor is to the sun, the brighter and easier it is to observe, but also the more it changes. Ice wakes, dust lifts, jets spin up and die down. After it swings past and fades, that activity quiets again. If you only measure early, you might call it wild. If you only measure late, you might call it plain. The right picture is a timeline. Harvard's real worry is simple. Miss one of the phases, and you will tell an incomplete story that later looks careless. That is the fear in our title, not a monster in the sky, but a gap in the record. There is also the opportunity fear, failing to ask a hard, answerable question while the window is open. Could radar ping it to estimate size? Could a radio dish listen for the faint hiss of water breaking apart? Could a chain of small telescopes, spread across time zones, watch a full spin without gaps? Each yes tightens the origin case. None requires wild leaps. They require coordination, quick scheduling, and the humility to pivot when a new data point disagrees. Consider spin. If 3i tumbles, its brightness will jitter in a way no simple shape can fit. That suggests a fresh nudge. Maybe a vent blew off center and gave it a twist. A calm, repeating rhythm suggests a settled body. Spin also controls how sunlight pushes it. A flat, thin object catches light like a sail. A compact one behaves like a pebble. By coupling spin with the tiny drift in the orbit, the team can estimate not only shape, but also how fluffy or dense the material might be. Dense rock shrugs off the breeze. A porous, powdery object feels it more. Finally, think about communication, the quiet choreography between caution and curiosity. In the early days, a sentence as simple as "its speed looks interstellar" must be paired with We need more nights to be sure. When color hints at deep cold chemistry, that hint should sit beside a reminder that thin clouds can trick the eye. This tone does not dull wonder, it earns it. It tells the audience, we are not afraid of being wrong. We are afraid of staying wrong once better data arrive. As the starry footage drifts by, wide, soothing shots of the sky, a pale crescent, a calm wash of nebula light, remember the stamp, speed and color, read with care. They are not the whole story of 3i divided by Atlas, but they are the first clear marks on its page. With them, a map to another star system begins to take shape, and the only fear that matters, the fear of missing the truth, starts to fade. Picture the first 72 hours after a strange alert lands in the inbox. A dot has shifted between two frames, and the software whispers, unbound path, likely. Phones light up, schedules bend, and a quiet relay begins. Verification comes first. Observers open the raw images and blink them like an old flipbook. Does the speck jump the way a real object should, or smear like a pixel scratch? Someone checks star catalogs so a faint galaxy isn't mistaken for motion. Another person reprocesses the frames with a second pipeline to catch hidden bias. If the motion survives, coordinates, times, and brightness go to a clearinghouse so telescopes on other continents can chase the target before it fades. Then geometry. Two eyes far apart see a slightly different position, a tiny effect called parallax. With that extra depth, the early path tightens. If the curve still looks open or a one-time flyby, then a loop confidence builds that we might be watching an interstellar traveler. If it curls into a closed oval, you treat it like a local comet or asteroid. That pivot is not defeat, it is good hygiene. Next, a heartbeat. A small telescope stares for an hour, taking a steady stream of short exposures. These fast snapshots turn into a light curve, the rise and fall of brightness as the object rotates. A calm, repeating pattern hints at a settled shape. A jittery one hints at a tumble or small vents puffing in sunlight. Either way, the heartbeat becomes a signature you can track night after night, even as the visitor grows fainter. Color checks arrive in parallel. Teams add simple filters: blue, green, red. If the object grows relatively brighter in red, that supports a dusty, weathered surface or a coma waking up. If it stays flat and gray across filters, you may be looking at darker rock. These are hints, not verdicts, but they steer what comes next. A redder glow may send infrared eyes to look for warm dust. A flat spectrum may push for radar or high-precision tracking. Choreography matters. Big observatories book months ahead, so someone writes a crisp plan, exposure times, filter choices, and the minimum needed to confirm unbound and to catch a coma if one is forming. The note goes out to partners across time zones. Amateur networks join too, because hundreds of small telescopes can paint a continuous timeline that a single giant mirror cannot. The playbook is simple. No hero shots, no wasted minutes, steady coverage. By the second night, cross-checks kick in. Data from different sites arrive. The team stacks images, smooths noise, and looks for a faint halo around the point. A coma can be subtle, only a hair wider than the sharp point of a star. You compare the object's shape to nearby stars taken in the same conditions. If it's consistently puffier, the case for a gassy coma grows. If it matches the stars, you lean rockward, while remembering that activity can switch on later as sunlight grows stronger. Now test for a tiny push that gravity alone does not explain. Sunlight pressure and venting gas both make small, predictable nudges. With 2 or 3 nights of precise positions, that extra drift can be teased out. If the numbers line up with heating from the sun, then active comet rises on the board. If the fit is odd, you pause and ask whether the tracking had subtle errors. The fear here isn't mystery. It's the trap of overinterpreting early, noisy data. While measurements flow, tone matters. Someone drafts the public note. Words like candidate, provisional, and pending confirmation aren't timid. They are safety rails that keep the story honest. Another teammate answers media calls and explains, in plain language, what the team knows and what it does not. Silence invites rumor. Careful speech builds trust. There is also the fear of missing the sweet spots. Activity can wake quickly as sunlight increases, then change again after the visitor swings past the Sunday. If you don't plan for both phases, you'll write a half-true story. A clean schedule early, near, and late solves this, as long as someone watches the clock and the weather. A quieter fear lives in the numbers. Tiny biases can steer the verdict. Warm cameras can redden faint objects. Thin, high cloud can fake a color trend. Small tracking errors can blur a coma into the background. Good teams assume such gremlins exist and go hunting on purpose. They switch cameras, sights, and filters. If the signal survives those swaps, it earns belief. What about the exotic ideas that crowd any interstellar headline? The responsible stance is simple. Put them on a shelf labeled "Only after ordinary tests fail." That isn't cynicism. It's how you keep wonder from turning into wishful thinking. Nature is already surprising enough when you let the data lead. If something truly odd remains after the usual causes are ruled out, the conversation can expand carefully, with clear predictions anyone can test. Visually, none of this needs flash. Slow star fields, a faint nebula, the curving limb of Earth at dawn. These calm images match the tone. The voice can move unhurried, even when the work is urgent. You don't need to rush to feel the stakes. You only need to keep the steps in order, like a pilot running a checklist. By the end of day 3, a verdict begins to form. Maybe the object is clearly interstellar and shows a gentle coma. Maybe it is an unusual, airless rock on a one-time pass. Maybe the early alert softens into a local visitor. Any honest result is a win because it sharpens our tools and reveals our blind spots. And if it is interstellar, the next chapters can ask the deeper question that hums under every frame. Once we know it came from another star, what can its path, color, and heartbeat tell us about the place it began? Think back to our 2 confirmed interstellar visitors. The first one, Oumuamua, slipped through like a riddle no classic tale. A faint extra push that didn't fit the usual playbook, and a light pattern that hinted at a stretched or flattened body. The second, Borisov, looked like a comet from another star, clear coma, steady gas, familiar physics. Those opposites became guardrails. When a new candidate like 3I Atlas appears, serious teams remember both cases at once and promise themselves one thing: don't marry a theory before the data can carry the weight. So what does fear mean inside a Harvard group watching a fresh alert? Not panic discipline. It is the memory that early curves can seduce, that a missing tail can fool, that a single telescope can lie. It is the vow to separate signal from wish. A dramatic light curve might be a lumpy rock spinning just right. A quiet object might still be venting gas you can't see yet. The cure is plain. Stack independent checks before you let your imagination roam. Because of that, the first deliverable is not a glossy picture. It's a shared checklist. Confirm the open, one-and-done path with independent astrometry. Build a light curve over several full spins so weather artifacts don't pose as physics. Sample color with simple filters, and, when possible, grab a quick low-resolution spectrum to sketch the rainbow. Compare the object's apparent size to nearby stars to sniff out a faint coma, fit for tiny drifts that the sun's heat could cause, and ask if those nudges rise and fall in step with warming. 2 underrated moves join that list. First, plan stellar occultations. The term sounds heavy, but the idea is simple. If the object crosses a star, the star blinks. Time that blink from several locations, and you can outline size and sometimes shape the way you'd trace a footprint with chalk. Occultations require luck and coordination, but they turn a fuzzy point into a silhouette. Second, try radar if geometry allows. Radar pings can reveal distance, speed, even hints of surface texture. It's not always feasible, but when it is, the payoff is clean numbers. There's also the quiet power of thermal watching. Infrared light lets you see warmth. If dust wakes, it glows like a stove ring in a dark kitchen. Pair that glow with the light curve, and you can separate a small, shiny object from a large, dark one. You can also learn how quickly the surface absorbs and releases sunlight clues to texture and porosity. None of this requires heavy math on air. It's just listening to different voices from the same traveler and asking them to agree. Timing cadence is everything. Early images catch awakening. Near-sun views catch peak activity. Late images catch the cool down. Miss a phase and you'll argue for months about what you never saw. That is a very practical version of fear. Not monsters, but gaps. Good cadence is boring to describe and priceless to own. It turns scattered snapshots into a story with a beginning, a middle, and an end, exactly what an interstellar visitor deserves. Communication should follow that rhythm. Use calm language that grows as certainty grows. You can share a light curve without sketching a dramatic shape. You can say no coma yet without implying never. You can note a small, consistent drift appears. We're testing ordinary causes first. These phrases do not kill wonder, they keep trust alive. The audience hears that curiosity is welcome and hype is not. That tone buys you patience while the measurements pile up. Someone always asks, could we visit it? Realistically, no. These objects are discovered late, move fast, and fade quickly. But even the no is useful. It forces rapid response plans you can reuse for the next surprise. It fuels designs for small interceptor spacecraft that sit ready in convenient orbits, waiting to sprint when an alert pops. You might not catch this one, but you can make sure the next window doesn't slam shut before a probe leaves the gate. Another temptation is to vault from a tiny push or odd light curve to grand claims. Responsible teams resist. Before you imagine exotic materials or engineered sails, you run the ordinary catalog: irregular shapes, patchy outgassing, porous surfaces that feel sunlight more strongly, fluffy dust clouds that spread force gently. Only after those are tested and still fail do you let the conversation widen, and even then, you frame ideas as questions with measurements that could confirm or kill them. That's not caution for its own sake. It's how you protect the truth. In that sense, Harvard's fear is really a promise. It's a promise to let independent checks decide which story survives, and to design the study so disagreement is a feature, not a crisis. Different instruments, different skies, different teams chasing the same effect. If all see it, confidence grows. If one does not, you find out why. Either way, the science gets stronger, and the public gets a clean, durable answer instead of a flashy maybes. All of this may sound procedural, but this is what honest discovery looks like. A calm checklist, a measured cadence, a few simple cross-checks. The humility to say, we don't know yet. When a candidate like 3i Atlas appears, those aren't the boring parts of the story, they are the story. They carry us from a blinking pixel to a clear picture of a traveler born around another sun, and they do it in a way anyone can follow. Before we let our imaginations sprint ahead, we should talk about how scientists keep from fooling themselves. The biggest fear in a careful room is not a monster in the sky. It is a quiet mistake that looks persuasive. With a candidate like 3i Atlas, the job is to prune those mistakes before they grow into stories. Start with the camera. Faint objects live at the edge of what a detector can see. A warm pixel can imitate a star. A cosmic ray can strike one frame and leave a bright dot that moves, only because the next frame has a different flaw. Software catches many of these, but trust does not come from code alone. People blink the images, swap filters, and change exposure times. If the point is real, it behaves in every setup. If it vanishes when you change the recipe, it was never there. Now the sky. Thin, high cloud can let more red light through than blue, faking a color trend. Compare the object to nearby stars in the same frame. If the whole field reddens, blame the sky. If only the moving point does, you have a signal worth following. Next, the clock. Rotation periods can mislead. Imagine a lighthouse on a rolling ship. The beam sweeps in and out while the deck tilts. If you sample at the wrong rhythm, you can invent a pattern that is not really there. Teams vary their cadence and combine nights from different longitudes. If the curve keeps the same pulse across schedules and sites, you are hearing the object, not your sampling. Backgrounds matter. A dim galaxy under the path can fatten the point and pretend to be a faint coma. The fix is simple. Check deep maps of the same patch of sky, align precisely, and subtract the background. If the puff remains, caution drops. If it disappears with the galaxy, you have learned a patient lesson and move on. Selection bias is another quiet actor. Surveys discover what they are designed to see. Fast, fresh arrivals get flagged. Slow, far, or dark ones slip through. Harvard's worry here is statistical, telling a grand story from a noisy choir. The answer is to say what your sample can and cannot represent, and to wait for patterns that repeat across several visitors. Rehearsal helps. Before trusting a pipeline on a new candidate, teams throw fake objects into old images and ask the system to find them. They vary speed, brightness, and color, and plant a few close to background galaxies. If the pipeline reports a hyperbolic path where none exists, they measure how often the method hallucinates. If that false alarm rate is 1 in 100, a single dramatic case deserves humility until independent data back it up. Another guardrail is blind analysis. Hide or scramble one key number while building your method so expectations cannot steer the result. Only after everyone signs off do you reveal the hidden piece and compute the answer. So, what would count as real trouble with 3i? One red flag would be a measurable non-gravitational push with no trace of dust or gas despite deep looks in visible and infrared light. Another would be a light curve that changes shape too quickly for simple rotation, as if the surface properties are flipping without cause. A third would be colors that disagree across instruments with no weather to blame. None of these proves anything exotic, but together they demand harder tests. Fortunately, sturdy cross-checks exist. Polarization, the way light's waves line up, can tell us whether we are seeing sunlight scattered by dust or bouncing off bare rock. Thermal watching in the infrared can expose warm dust even when visible images look clean. Occultations can pin down size, so we stop guessing whether a bright point is small and shiny or larger and dark. And radar, when geometry allows, can give distance and drift so clean that small forces cannot hide. Across all of this runs a single thread: replication. Different teams, different tools, same sky. If they agree, you can stand taller. If they disagree, you do not pick a winner by charisma. You find the cause. Maybe one camera was warmer, one sky thinner, one clock slightly off. The moment you learn why, a worry turns into a fix, and the next object benefits. Why care so much? Because interstellar visitors are free samples from other solar systems. We will not reach another star soon, but chips from other kitchens drift through ours. Each one carries a hint of the pantry it came from, how its ice is formed, how its rocks weathered, how often big planets sling small bodies into the galaxy. These are not abstract details. They fold into the larger story of how worlds build and how often they settle down. That is the quiet heart of the Harvard fear. The fear of letting a rare sample slip through our fingers, or worse, of wrapping it in the wrong story. Both mistakes steal from the future, one by absence, the other by noise. The antidote is simple language, steady cadence, and a habit of asking ordinary questions first. Is the path open? Is the color real? Is the coma there when the galaxy is gone? Does the tiny push rise with the sun? If the answers line up, confidence climbs. If one answer wobbles, we do not hide it. We say so and tighten the plan. That is not an apology. It is a promise that the truth matters more than a headline. And in a field that catches one interstellar traveler every few years, that promise is how we earn the next one. Settle in. The mystery is not a sprint. It is a walk under calm stars. Each careful step checking the pixel, checking the weather, checking the timing, sounds small on its own. Together, they draw a clean path through the noise, so that when we finally say what Three-Eye Atlas really is, the words can carry the weight that wonder deserves. Imagine Three-Eye Atlas as a sealed jar from someone else's kitchen, tossed over the fence and landing in our yard without a label. We can't open it, taste it, or keep it for long. But we can lift it to the light, tilt it, feel how it warms, and listen for the faintest fizz. That is what composition work looks like from Earth. Patient, indirect clues anyone can follow. Begin with space, weathering the slow sunburn that darkens and reddens surfaces left out for ages. Sunlight and a drizzle of tiny impacts roughen skin and bake dust. If Three-Eye grows relatively brighter in red filters than in blue and keeps that tint night after night, the surface may be layered with weathered grains, the patina of a long, cold journey. If the color stays neutral as it warms, that hints at fresher crust or darker rock. Texture comes next because sunlight treats fluff and stone differently. A compact rock behaves like a polished pebble. A powdery surface acts like felt. When light hits fluff, it can sink in a bit, heat slowly, and release warmth long after sunset. Infrared eyes, the ones that see heat, catch that lag. Pair this gentle warmth with the rhythm of the light curve, and you can tell whether our jar is thick or thin, whether it holds gravel or flour. Dust, if present, is both clue and challenge. A soft coma smooths the light curve and makes everything look a little larger and gentler than it really island. But the dust itself carries information. Fine grains scatter light like fog, spreading a broad, even glow. Larger grains act like glitter, throwing sharper highlights that change with angle. By watching how brightness shifts as the sun object Earth geometry changes, teams can estimate average grain size without ever catching a speck. Gas tells a different truth. Water vapor, carbon dioxide, and other ices leave faint, specific fingerprints, tiny dips or bumps in the spectrum, like barcodes. Even a quick, low-resolution spectrum can hint at which ices wake first. If water dominates, we're likely seeing a body born in a zone like our own comet nurseries. If more exotic ices whisper in the signal, perhaps the object formed even farther from heat, in a deeper cold where only certain molecules can freeze. Now picture 3 clean outcomes, and what each would mean. First, the deep cold comet. A clear coma, a reddish tint that grows with warming, a tiny push that rises when sunlight hits. Hardest classic behavior for an icy traveler slung out by a giant planet, a cousin of 2I Borisov with new chemistry to compare. Second, the dark rock. No coma near peak warmth, flat colors, a steady light curve, and little drift, likely a dense compact shard. Third, the mixed case. Brief, patchy activity and small, fading pushes, vents switching on and off, crust cracking, or big grains falling back toward the surface. Each ordinary cause has a test. Watch longer, watch in heat, watch from more than one angle. Compare the object's shape to nearby stars to control for sky tricks. Harvard's discipline is to run those tests before reaching for exotic ideas. That is the culture behind the word fear in our title. The fear of telling an avoidable wrong story. Meteor watchers add a crafty wrinkle. If Three-Eye sheds dust and Earth later passes through that stream, the sky could host a faint new meteor shower with unusual speed. Radar and sensitive cameras might catch those streaks and, from their brightness and plunge, estimate grain strength and density. It's a long shot and needs lucky timing, but it turns the upper atmosphere into a sampling net, a brief way to open the jar without touching the traveler. There is also value in the quiet no. If repeated, careful spectra show little or no gas, that absence is information. If infrared warmth never rises above what bare rock would show, that's a result, not a disappointment. Science advances on clean negatives as much as on bright positives. They map the range of what interstellar debris can be, and prune theories that try to make every visitor behave the same way. Why dwell on composition? because it ties to big questions people care about. How planets build, how water travels, and how often delivery trucks of ice and dust crisscross young systems. If travelers like 3I are mostly icy, that supports a galaxy where far-flung comet clouds are common, and giant planets often fling samples into space. If many are rocky, that hints at violent inner zones where collisions chip and throw. Either way, each visitor turns a guess into a trend. Communication should stay simple. You can say, "We see a faint reddish halo dust waking as sunlight warms the surface," or "No gas so far, even in infrared," which makes rock more likely. You can add that a tiny non-gravitational nudge rises with heat supporting ordinary venting, or that no such nudge appears, keeping the picture plain. These sentences are kind to sleepy listeners and honest to the data. None of this needs flashy visuals, slow pans of a comet in silhouette, star fields drifting, a quiet crescent sliding by frames that match the voice and leave room for thought. The aim is not to overwhelm, it is to invite. The more people can picture the simple tests, color, warmth, rhythm, the more they can feel the stakes without a textbook. Hold the jar one more time, tilt it, and notice how the light inside changes. Warm it a little, and see whether anything stirs. Listen for fizz. Every clue is small. Together they make a map. That map won't give us the name of the star that made 3I Atlas, but it will tell us what kind of shelf it came from, and what kind of pantry threw it our way. For a visitor we will never touch. That is enough to change how we think about the space between stars. Rewinding the path of a traveler is like trying to find the splash point of a stone after the ripples have spread. With a candidate like 3I Atlas, the stone is small, the pond is the solar system, and the ripples are tiny forces that push it as it flies by. Still, astronomers try. They take the measured positions dots with timestamps and run the clock backward, step by careful step, until the object is far from the sun's pull. That gives a clean incoming track, a direction in the sky, and a speed before our gravity bent it. Think of it as the arrow on a map that says, "Arrived from here." The next move is bold but simple to explain. Compare that arrow with the motions of nearby stars. Our best star maps come from the Gaia mission, a careful census of the Milky Way that tells us how stars drift. If the backtracked path of 3I passes close to a known star in the recent past, close in space and time, then that star becomes a candidate parent. Maybe a big planet there flicked the object out, or a close stellar encounter shook loose a handful of icy bodies. The idea is not to claim a birth certificate, but to find neighborhoods that fit the direction and speed we measure. Here is where the fear hides. Small errors grow. If you have even a tiny uncertainty in the object's position or the gentle pushes it felt near the sun, the backtrace blooms from a narrow line into a wide cone. Rewind a little too far with the wrong push, and you could point at the wrong neighborhood. That is why teams prize early, precise measurements. Before the sun's warmth wakes any jets, and before tiny nudges stack up, the path is simplest. Miss that phase and the cleanest clue to origin blurs. The nudges themselves are common sense physics. Sunlight warms one side more than the other. A jet of vapor might puff from a crack. Dust might act like a tiny sail. None of these forces is strong, but over weeks they add up. Picture a leaf drifting down a slow river, while small breezes push it toward one bank. If you try to rewind the leaf's path without knowing the breeze, you might blame the wrong branch for the drop. Harvard's caution lives here. Do not draw a straight arrow through a messy wind. Even with that caution, there are patterns to hunt. If interstellar visitors tend to arrive with similar speeds relative to the local flow of stars, that hints at common launch mechanisms. Giant planets in wide orbits are good at flicking out comets. Binary stars, two suns bound together, shake their outskirts and spray debris more easily. Young star clusters, where stars are born in groups, are noisy neighborhoods where close passes are frequent and ejections more likely. Each scenario leaves a different imprint on the speeds and directions of the bodies that escape. Backtracing blends with storytelling here. but the stories stay testable. If 3I's incoming speed and color match what we expect from deep cold comet zones, then stars with long-period giant planets and big outer reservoirs become better bets. If it looks rocky, stars with crowded inner systems and lots of collisions climb the list. If its path lines up with a known stellar stream, groups of stars that drift together through space that suggests a shared history in the same nursery long ago. There is a logistical fear too, missing the rare chances to sharpen that arrow. Certain measurements are time-sensitive. Occultations by the object, when it briefly blinks out a star, can pin down size and help fix how sunlight pushes it. But they happen along a thin path across Earth, like a moving shadow. You need quick coordination and luck with weather. Radar, if geometry allows, offers distances so clean they crush uncertainty, but the window can be just a few nights. If you are slow with these, the door shuts, and your map of arrived from here stays fuzzier than it had to be. Communication choices feed into this. Backtracing results come with probability clouds. This neighborhood is more likely, that one less. Say it plainly, do not oversell a favorite star. Do not hide when a new measurement widens the cone. The public can handle gray if you paint it honestly. In return, you earn room to revise without whiplash headlines. That tone is not just style. It protects the science from being boxed into a story too early. Citizen observers help more than people realize. A chain of small telescopes can nail the rotation period and gather the long, steady light curves that big observatories have no time for. When folded into the orbit solution, that steadiness shrinks errors. Amateurs can also be mobile for occultations, driving to where the shadow will sweep. Interstellar objects are fast and faint. The difference between "we tried" and "we got it" is often a car on the right road at the right hour. One more subtle point matters when we talk about origins. The galaxy itself is not a calm stage. Stars orbit the Milky Way on different lanes and tilt slightly up or down through the disk. Gas clouds drift. Spiral arms tug. Over millions of years, those slow shifts blur any attempt to rewind far, so origin work is about recent history, tens of thousands of years at most, not about claiming a birthplace eons ago. That frame keeps expectations sane. We can find likely neighborhoods, not home addresses. What if the backtrace refuses to settle? That result is still a result. It might mean the non-gravitational pushes were larger than expected, or that activity switched on and off in a way that hides the clean incoming vector. It might simply reflect that we met the traveler late and tracked it for too short a time. The lesson then is practical. Design surveys and response plans that catch the next one earlier, measure it longer, and leave a tighter arrow on the map. Through all of this, the Harvard fear keeps its honest shape. It is the fear of naming the wrong neighborhood and watching that mistake fossilize in printouts and posts. It is the fear of skipping a measurement that would have closed the cone by half. And it is the fear of letting a tidy headline outrun the messy truth. The antidote is familiar by now. Early precision, cross-checked methods, open probabilities, and a schedule that treats rare windows like gold. As the visuals drift broad starfields, a slow pan across a galactic arm, a soft glow at a horizon, hold the map in your mind. An arrow, a cone, a handful of likely neighborhoods. That is the scale at which origin becomes real for a visitor we will never touch. And if 3i Atlas teaches us how to draw that arrow a little sharper, the next traveler will arrive to find us ready. If 3i Atlas is a message in a bottle, what could nature have written inside? Not poetry or symbols, just ratios, rhythms, and colors that quietly tell us where and how it formed. This chapter is about those wish list measurements that turn a one-time visitor from a curiosity into a data point that reshapes our charts. Start with water. All water is not the same. A tiny fraction of water molecules are heavier because one hydrogen is the heavy kind. The mix between normal and heavy water acts like a climate tag from the bottle's birthplace. Colder nurseries make a different mix than warmer ones. We cannot scoop liquid from 3i, but we can watch for faint fingerprints from water split by sunlight near the object. If we detect that pattern and compare heavy to light, we learn something solid about the pantry it came from. Other simple fingerprints matter. Carbon-bearing gases leave one kind of mark, nitrogen another. A whiff of carbon monoxide often points to deep cold. More common fragments hint at ice that has been warmed before. Even at a soothing, sleepy pace, the idea is easy to carry. Different ingredients light up different shelves in the cosmic kitchen. A short spectrum, just a smeared rainbow with a few bumps, is enough to begin that recipe list. Dust can be read like tea leaves. Fine, smoky dust scatters light smoothly, making the halo around the core look soft and broad. Grittier dust throws sharper sparkles and fades differently as the viewing angle changes. If 3i lifts dust, we can watch how the halo swells and shifts and infer the average grain size, the way a baker guesses flour versus sugar by how a pinch falls through the air. Grain size tells us about the crust that held it tight and crusty, or fragile and fluffy, and how sunlight might have processed its surface over time. Then there is the rhythm of the spin. A clean, steady beat means a calm, settled body. A stumbling beat means tumble, vents, or an odd shape. Pair that rhythm with how the object brightens as it nears the sun, and you can pick between an airless rock and an ice that wakes. Picture a porch light on a timer. If the light grows not only because you walk closer, but also because the bulb gets stronger, then something inside is turning on. That is what activity looks like, and catching that switch on is worth gold. Thermal, watching the art of measuring warmth, adds a quiet but powerful voice. A dark surface warms quickly and releases heat like a stovetop. A bright, reflective surface warms less. Powder holds heat longer than polished stone. If an infrared eye sees a warm blush lagging behind sunset on 3i, the jar likely holds fluff. If warmth rises and falls quickly, it likely holds denser stuff. With warmth and the light curve together, teams can estimate not only size and reflectivity, but also whether the surface behaves more like loose powder or a tight crust. Now the tension. Some of these checks are possible only during brief windows. You need the object bright enough for a spectrum, but not so close to the sun that glare drowns the signal. You need the right geometry for radar and the right path across Earth for a stellar occultation. The fear inside any Harvard plan is missing one window and losing a whole branch of the story. So the schedule looks like a racing line through a set of gates. Hit each gate once, cleanly, and move on. Early images catch awakening. Near-sun views catch peak behavior. Late phase looks catch the cooldown. Why not leap to the spicier questions, techno-signatures, engineered materials, signals? Because discipline is a friend, not a cage. Responsible teams do two things at once. They run the natural tests first, and they listen in the background. A radio dish can scan for narrow, unnatural tones while others take images. Software can search for odd flicker patterns while people measure the coma. If nothing odd appears, that quiet no is a clean result. If something does, it stands out against the careful baseline that ordinary physics built. Communication can stay gentle. Instead of saying, "We measured heavy water at a specific ratio," you can say, "The water looks more like what we see from deep cold shelves than from warm ones." Instead of, "The thermal inertia suggests porous." Regolith, you can say, "The surface behaves like powder rather than smooth rock." Translate the lab into kitchen and garden. Keep the voice calm, and the audience stays with you without strain. There is also what we learn by absence. If 3i shows no gas despite deep looks and no extra push beyond gravity, that sets limits. Either it is a rock with little to give, or any ice hides under a hardened crust. If dust appears only briefly and then stops, maybe sunlight sealed the cracks, or the jets were small and patchy. In each case, the negative result trims the set of origin stories and makes the next visitor easier to read. Clean no answers are not boring. They are rails that keep speculation from drifting. Think about what a trend would mean once we have more than 2 or 3 visitors. If the next handful all look like Borisov, icy, active, familiar, then comet clouds are probably common around other stars. If a surprising number look like bare rocks, then inner system collisions and ejections might dominate. If there is a split, half and half, that says different planetary systems throw different debris, the point is that 3i is not just a headline, it is a dot on a growing plot. A dozen dots give a pattern becomes a story we can trust. Finally, honor the limits. There are things we cannot know from afar. The exact shape without an occultation, the exact size without radar, the deep interior without a probe. It is okay to say so. Honesty builds trust, and trust is the only bridge strong enough to carry people from a dot moved to we learned something about another sun's pantry. The promise under the Harvard fear is simple. We will not shrink from the wonder, but we will let the ordinary tests speak before we invite extraordinary claims. As the visuals drift starfields, a slow turn over a pale crescent, a faint glow of a nebula. Remember the bottle in the surf. We cannot uncork it, but we can weigh it, warm it, listen, and read the stains on the glass. Do that well, and the message inside becomes clear enough to change how we see the sea between stars. Think of this chapter as the calm nerve center of the entire effort. 2 clocks tick at once. The sky's clock never pauses. Our visitor moves, brightens, and fades on its own schedule. The public's clock buzzes, attention spikes, rumors spread, and people want answers now. Harvard's practical fear lives between those clocks. Move too fast and you risk saying more than the data allow. Move too slow and you miss the narrow windows that turn a guess into knowledge. The only way through is a simple, repeatable playbook. 4 verbs carry it: confirm, characterize, coordinate, communicate. Confirm comes first. It means independent detections from different telescopes at different sites. It means showing that the path is truly open, shaped like a hyperbola so wide it will not loop back. It also means cleaning away easy mistakes, background galaxies that can puff up the dot, warm sensors that tilt colors red, timing drifts that fake a wobble. When these checks all agree, the word candidate quietly gives way to interstellar visitor, not by opinion, but by accumulation. Characterize is next. Here, the visitor stops being a nameless dot and gains a sketch of personality. Speed tells where it sits in the local traffic of our star neighborhood. Color hints at surface chemistry. And dust, the light curve, the rise and fall in brightness as it spins, hints at shape and stability. Infrared warmth reveals texture. Powder holds heat. Polished rock sheds it. None of these facts is dramatic on its own. Together, they prune wild stories and leave a few sturdy options anyone can follow. Coordinate turns one group into many. Big observatories provide sharp, deep looks but cannot keep watch all month. Small telescopes can stitch together the nightly heartbeat. A radio dish can listen for familiar molecules, while an optical scope images. If geometry is kind, radar can ping and lock the distance like a ruler. Occultations, the brief blink when the traveler crosses a star, can pin down size and even outline shape. The fear here is mundane but real. Missing a one-time chance because weather or timing gets in the way. Communicate runs the entire time. It is not a press stunt, it is part of the science. Clear updates keep other teams from repeating dead ends and invite help where the gaps are. A good note sounds like this: unbound path remains likely. No coma detected yet. Slight reddening appears consistent across sites. Next steps: infrared checks and a search for a small non-gravitational push. Plain words buy patience. They also protect trust when numbers change, as they often do. Under this playbook sits a culture choice: accuracy over applause. Delivered with warmth, that means translating without dumbing down. Instead of multiband photometry shows reddening, say it reflects a bit more red light than blue. Instead of low thermal inertia, say the surface behaves more like powder than smooth stone. The ideas stay strong, The sentences get friendly, so sleepless listeners can follow without strain. There is also a budget of time and attention. Every hour reprocessing early frames is an hour not spent planning radar or mapping an occultation line, so the team keeps 2 lists. Quick wins fix big uncertainties fast. Extra positions to lock the orbit, a 1-hour light curve to catch the spin, a simple 3-filter color check to flag obvious trends. Heavy lifts take luck and planning, thermal maps near peak warmth, radar passes, deep spectra hunting faint gas. Quick wins guide where to spend the heavy lifts wisely. An ethical lane runs alongside. Interstellar objects attract exotic ideas. Responsible teams do not mock curiosity, they frame it. You can say, some wonder if odd pushes could come from unfamiliar materials. Before we go there, we test ordinary causes like jets of gas and sunlight pressure. If those fail, we will say so and show the numbers. This stance protects wonder from hype and keeps the door open for surprises without promising any. Ownership is simple. Discoveries belong to everyone. Positions should flow quickly to the common clearinghouse, so the orbit tightens. Shared light curves help decide whether a flicker is physics or weather. When an answer finally settles, credit is broad survey crews, follow-up observers, analysts, software people, and schedulers. The failure to avoid is a private storyline that collapses when others finally see the data. From the audience's side, trust grows when limits are spoken aloud. Some things cannot be known from afar. The deep interior, the exact shape without a lucky blink, the birthplace beyond a neighborhood. We don't know yet is not hedging, it is honest alignment with the sky's clock. The reward for that honesty is room to revise as better numbers arrive. All of this caution may sound slow, but care is not delay, it is order. Order lets fast work happen in the right sequence. With 3 ITLAS, that sequence turns fear into fuel. We fear missing a window, so we schedule across time zones and seasons. We fear fooling ourselves, so we cross-check with different instruments under different skies. We fear misleading people, so we write updates that are short, true, and testable. Put together, those fears become a steady engine that carries the story forward. And if the verdict ends up simple rock, not ice, unbound, not bound, do we still celebrate? Absolutely. Simple outcomes drawn from disciplined, well-timed work are wins twice over. They sharpen tools, refine playbooks, and make the next mystery easier to read. The sky's clock will keep ticking, the internet's clock will keep buzzing. Between them, a small team that chooses care over noise can still catch a truth as it slides by and share it so anyone can understand. Hold that center as we move on. In the next section, we will apply this toolkit, confirm, characterize, coordinate, communicate, to a handful of concrete what-if cases for 3I Atlas, so the mystery stays vivid yet grounded, while the stars drift quietly across the screen. What if we run the playbook on a few concrete paths for 3I Atlas? Picture them as branches on one tree. We'll walk each branch slowly, in simple steps, so even a sleepy listener can follow without strain. Case 1, the classic deep cold comet. Early frames show a faint, steady halo around the point. Simple color checks lean redder with time, a hint that dust is waking. The light curve keeps a calm beat, like a slow, repeating drum. When teams fit the orbit, a tiny extra drift appears and grows as the object warms, the pattern you get when gas jets push gently. Infrared views add a soft blush that lingers after local sunset on the surface, the signature of powder that holds heat. In this branch, the call is clean, an icy traveler stirred by sunlight. The lesson we'd learn is practical and big. Comet clouds around other stars really do throw samples into the galaxy, and our instruments can read those samples from across space. Case 2, the airless shard. Night after night, the point looks as sharp as nearby stars. With no puffier edge, the color stays gray across filters. The light curve repeats with a neat rhythm, and only a small swing, the sign of a compact shape. No extra push appears beyond gravity. Infrared warmth rises and falls quickly. like rock that sheds heat rather than powder that holds it. This branch says dense fragment, likely chipped from an inner zone by a violent collision and then flung away by a close pass with a big planet. The takeaway is different, but just as useful. Rocky debris can also escape star systems and drift between suns, so the space between stars is not only icy, it can be stony too. Ownership is simple. Discoveries belong to everyone. Positions should flow quickly to the common clearinghouse, so the orbit tightens. Shared light curves help decide whether a flicker is physics or weather. When an answer finally settles, credit is broad survey crews, follow-up observers, analysts, software people, and schedulers. The failure to avoid is a private storyline that collapses when others finally see the data. From the audience's side, trust grows when limits are spoken aloud. Some things cannot be known from afar. The deep interior, the exact shape without a lucky blink, the birthplace beyond a neighborhood. We don't know yet is not hedging, it is honest alignment with the sky's clock. The reward for that honesty is room to revise as better numbers arrive. All of this caution may sound slow, but care is not delay, it is order. Order lets fast work happen in the right sequence. With 3 ITLAS, that sequence turns fear into fuel. We fear missing a window, so we schedule across time zones and seasons. We fear fooling ourselves, so we cross-check with different instruments under different skies. We fear misleading people, so we write updates that are short, true, and testable. Put together, those fears become a steady engine that carries the story forward. And if the verdict ends up simple rock, not ice, unbound, not bound, do we still celebrate? Absolutely. Simple outcomes drawn from disciplined, well-timed work are wins twice over. They sharpen tools, refine playbooks, and make the next mystery easier to read. The sky's clock will keep ticking, the internet's clock will keep buzzing. Between them, a small team that chooses care over noise can still catch a truth as it slides by and share it so anyone can understand. Hold that center as we move on. In the next section, we will apply this toolkit, confirm, characterize, coordinate, communicate, to a handful of concrete what-if cases for 3I Atlas, so the mystery stays vivid yet grounded, while the stars drift quietly across the screen. What if we run the playbook on a few concrete paths for 3I Atlas? Picture them as branches on one tree. We'll walk each branch slowly, in simple steps, so even a sleepy listener can follow without strain. Case 1. The classic deep cold comet. Early frames show a faint, steady halo around the point. Simple color checks lean redder with time, a hint that dust is waking. The light curve keeps a calm beat, like a slow, repeating drum. When teams fit the orbit, a tiny extra drift appears and grows as the object warms, the pattern you get when gas jets push gently. Infrared views add a soft blush that lingers after local sunset on the surface, the signature of powder that holds heat. In this branch, the call is clean, an icy traveler stirred by sunlight. The lesson we'd learn is practical and big. Comet clouds around other stars really do throw samples into the galaxy, and our instruments can read those samples from across space. Case 2. The airless shard. Night after night, the point looks as sharp as nearby stars. With no puffier edge, the color stays gray across filters. The light curve repeats with a neat rhythm, and only a small swing, the sign of a compact shape. No extra push appears beyond gravity. Infrared warmth rises and falls quickly, like rock that sheds heat rather than powder that holds it. This branch says dense fragment, likely chipped from an inner zone by a violent collision and then flung away by a close pass with a big planet. The takeaway is different, but just as useful. Rocky debris can also escape star systems and drift between suns, so the space between stars is not only icy, it can be stony too. Case 3. The patchy waker. At first the object is quiet. Then, as sunlight grows, a faint coma switches on for a few days and fades. The light curve jitters like a weak heartbeat, as if small vents turn on and off. A mild non-gravitational drift shows up only near peak warming. Infrared hints at warm dust, but not much. This mixed behavior has ordinary causes: a crust that cracks at stressed spots, big grains that fall back, pockets of ice trapped under a hardened skin. Here, cadence is king. You schedule early, near sun, and late phase checks, so you catch the on, the middle, and the off. If you miss one phase, the story bends the wrong way. Case 4. The odd push, with no obvious dust. The orbit fit shows a small extra acceleration, yet deep images and infrared views find no coma. Before anyone reaches for exotic ideas, teams tighten ordinary checks. Could sunlight on a very porous, low-density body create more sail effect than expected? Could tiny gas sprays hide under a crust and leave only a thin, hard-to-see plume? Polarization measurements test for hidden dust. Thermal data look for warmth that bare rock would not have. A blind analysis hides one key number, so expectations cannot steer the result. If, after all that, a push remains with no visible dust or gas, the proper tone is not shock, it's clarity. We see a small, repeatable drift. Ordinary causes are strained but not ruled out. Here are the next measurements that can settle it. Case 5. The shape illusion. A huge light curve swing tempts people to imagine a needle or a flat disc, but sampling can fool you. If you always observe at nearly the same viewing angle, a lumpy potato can masquerade as an extreme shape. The cure is simple. Gather a full rotation from different longitudes so the rhythm can't fake a pattern. If luck allows, catch a stellar occultation so a clean silhouette breaks the tie. If the swing survives all that, you accept an odd shape without drama. Nature loves variety. We don't need a movie plot to enjoy a strange rock. Case 6. The rare geometry gift. Sometimes the path brings the visitor close enough for radar, or sets up a clean occultation across a wide landmass. Those chances are gold. Radar distances shrink orbit errors and reveal drifts so small that other methods would miss them. Occultations, sketch size, and, with chords from several sites, even outline shape. If either gate opens, the plan pivots to seize it, because one clean pass can collapse a month of maybe into a week of yes. The practical fear here is missing a one-time window. The fix is a standing plan that can move people and instruments quickly. Now fold branches back into origin. A comet-like 3i points to distant shelves around its parent star and says that giant planets there are good at clearing their yards. A rocky 3i points to busy inner zones where collisions and close passes are common. A mixed 3i suggests skins that harden with age, then crack under stress. Track the incoming direction and speed against precise star maps, and certain neighborhoods rise in likelihood: young clusters for noisy ejections, wide-orbit giants for clean flicks, binaries for steady shaking at the edges. You won't get a street address, but you can circle a part of the sky with honest confidence. Communication hardly changes across branches. Keep the lines short and the claims testable. Unbound path confirmed. Faint coma appears. Dust is likely. No non-gravitational drift yet. Infrared warmth lags sunset, which argues for a powdery surface. These sentences are friendly to tired ears and sturdy enough for scientists to stand on. They also leave room to turn the wheel as the picture sharpens, which is how you protect trust when new numbers nudge the plot. And the Harvard fear, it dissolves into planning. Fear of hype becomes a checklist of ordinary causes to exhaust. Fear of missed windows becomes a schedule that guards a few crucial nights. Fear of being wrong becomes language that lets better data change the story without whiplash. None of this dims the wonder. If anything, it makes the wonder safe to share, because the path from spec to sentence is clear enough for anyone to walk. Whichever branch reality chooses, the traveler leaves a mark. A clean comet makes other suns feel neighborly. A quiet rock proves our surveys can catch hard targets. An odd push nudges our models to grow up. The point is not to force a headline. It is to earn a solid line that will still be true when the next visitor drifts in. That is how a small object from far away becomes a large step in how we read the space between stars. Think about the moment a rumor outruns a result. A single dramatic phrase alien probe can sprint across feeds faster than a careful sentence like, "No coma detected yet." That is the tightrope any serious group walks when a candidate like 3i Atlas appears. The fear is simple. If the story catches fire before the numbers settle, people remember the spark, not the truth. So the work adds a second layer most viewers never see, building a calm channel that carries updates without the noise. Inside a university lab, that channel starts with language. Terms are chosen on purpose. Candidate means interesting but not confirmed. Preliminary means we expect the values to shift. Provisional designation means the name can change as the orbit sharpens. These are not hedges, they are promises that better data will be allowed to speak. Beside those words sits a short list of myth checks. If someone asks whether brightening proves engines, the answer is simple. Sunlight warming fresh ice can make dust and gas that brighten an object without anything artificial. If someone points to a tiny push as proof of control, the reply is straightforward. Outgassing and sunlight pressure can nudge small bodies in ways our models can track. A second tool is a traffic light board. Green items are facts confirmed by independent teams. Yellow are hints worth chasing. Red are claims with no supporting data. The board is public and updates on a steady cadence, even when the update is no change. That rhythm turns curiosity into patience and teaches people to expect small, honest steps. Media outreach is not a press parade. It is a classroom without grades. A good briefing leads with what is known, lists 2 or 3 crisp questions for the next observing window, and shows which instruments are aimed at them. When numbers shift as they will, the follow-up explains what changed and why. Better timing, cleaner skies, a longer light curve, or a new wavelength added to the mix. Students are the heartbeat. They align frames, measure star shapes, test filters, and draft the first updates. A senior scientist checks tone and detail. The fear they carry is healthy. The fear of wasting other people's telescope time with sloppy requests. That fear produces clarity. Exposure times are listed. Filters are justified. Success criteria are stated up front so a partner can say, "Yes, we can get that." Or, "Clouds tonight, try the other site." Open data quiets storms. When positions, brightness, and basic processing notes flow quickly to the community network, duplicates and dead ends shrink. Openness also lets independent groups try to reproduce any subtle effect, like a tiny push or faint reddening. Agreement across teams is the real antidote to hype. If a claim survives, different software, different skies, and different clocks, it deserves to live. If not, it dissolves without drama. On social media, the tone stays plain. Short posts use concrete nouns and verbs. Unbound path still likely after tonight's measurements. No dust in infrared. Rock remains plausible. A small extra drift appears. Ordinary causes are being tested. Each post links to the longer board, so context is one tap away. The rule is gentle. Never dunk on a wild claim. Never tease a result. Never promise a reveal. Curiosity is welcomed. Certainty is earned. A housekeeping lesson runs underneath. Log everything. Log when a frame was taken, who processed it, which version of code built the light curve, and what the sky looked like that hour. Logs let you rewind a mistake without blame and show exactly why a value changed between Tuesday and Friday. Boring to write. Priceless when the spotlight turns. Edge cases will appear: the odd push with no dust, the light curve that flips, the color that refuses to match across sites. Here, the best friend is a pre-written ladder of tests. Each rung is finite and specific. Repeat the color checks with a different detector. Run a blind analysis with the key constant hidden. Try polarization for hidden dust. Ask a second site to observe at a different phase angle. If the effect survives the ladder, it earns a bolder sentence. If it dies on a rung, you thank the ladder for saving you from a wrong turn and move on. Trust is the true currency. Trust with the public, trust between teams, trust in the method. It is built with small habits, admitting limits, sharing raw numbers, answering basic questions without sighs. The fear at Harvard is losing that trust by talking past the data or by speaking so slowly that the moment slips. The cure is a measured voice, quick enough to catch the windows, careful enough to leave every claim resting on a number anyone can check. As our calm footage drifts star fields like powdered sugar on velvet, a thin crescent, a quiet sweep over a nebula, remember why this layer matters. Discovery is not only the sky. It is also the path a fact takes from a sensor to a sentence. If that path is clean, the wonder at the end of it can be shared without apology. If it is messy, the wonder curdles into noise. With 3-eye atlas, the goal is simple: keep the path clean. So whatever the verdict is, icy, rocky, mixed, or odd, will stand when the feeds move on and the headlines fade. This is the culture hidden under the word fear in our title. It is not fear of the unknown. It is fear of wasting a rare visit by telling the story badly. Language, cadence, logs, ladders, and open doors, none of these shine on a poster, but together they protect the truth. And when the truth is steady, people can relax into the mystery instead of wrestling with rumors. Think of the galaxy as a quiet sea lane and of small bodies as driftwood from far shores. Every so often, a piece floats past our beach. If we only stare at one log and argue about its shape, we miss the bigger truth. The tide itself has a pattern. A careful team at Harvard or anywhere does not only ask, "What is 3-eye atlas?" It also asks, how many of these travel by each year? How big are they on average? What mix of icy and rocky do we see? Which lanes do they prefer? The fear hiding here is simple and honest. If we treat each visitor as a one-off spectacle, we will miss the trend that tells us how other solar systems really work. Trends begin with counting, and counting requires consistency. That means logging every candidate down to the same simple facts: when it was seen, how bright, how fast, which direction, how the light rose and fell, whether any dust showed, and whether a tiny extra push appeared. Most of those facts can be measured with modest telescopes if you plan ahead. The point is not glamour, the point is rhythm. 10 clean visitors described in the same way will teach more than one famous oddball described in poetry. Rates matter because they point to engines. If interstellar visitors arrive more often than we expect, something out there is flinging debris efficiently, perhaps giant planets in wide orbits, or binary stars that shake their outskirts. If they arrive more rarely, ejection may be slower and quieter than our models predict. Either answer is useful. It moves us from stories to statistics, from maybe to likely. Sizes matter because small and large travelers obey different rules. Pebble-scale bodies feel sunlight pressure more and crumble more easily. Boulder-scale bodies hold heat longer and keep their spin steadier. If the visitors we detect cluster at small sizes, that tells us our surveys are still shallow. If we find a spread, that tells us we are sampling the real population. The fear here is sneaky, a biased sample that looks like a law. The cure is to write down our limits in the same breath as our claims, and to upgrade them as new surveys come online. Composition trends matter because they feed the big questions: how planets gather water, how crusts form, how common deep cold shelves are around other stars. If most travelers look like icy cousins of Borisov, the galaxy may be rich in comet clouds. If many look like bare shards, then inner system collisions and close passes may be the main export engines. A split result would be the most interesting of all, because it would say planetary systems are not one recipe, but a family cookbook with regional flavors. Now, imagine a very practical shelf in that quiet Harvard office, a next time kit. On it sits a short radar request template with exposure times already tested. A one-page occultation playbook shows how to draw the shadow track across Earth and who to call in each region. A standing agreement with small telescope networks can start a 12-hour light curve with one email. A set of gentle public phrases is ready to go, so the first update sounds calm, clear, and consistent. Fear becomes readiness when a plan is within reach of one hand. There is also the dream shelf, the interceptor idea. We will not chase this visitor. These objects are found late and move fast. But the blueprint exists for tiny, off-the-shelf probes that can wait in space, powered and patient, until an alert pops. Then a small kick sends one sprinting for a flyby. Even if that sprint misses this year, the design work is not wasted. It becomes a seed others can grow. Faster launches, smarter cameras, lighter spectrometers. A team that says, not this time, but soon, is not dodging, it is building. Numbers must live alongside stories people can hold in a sleepy mind. That means translating each trend into a picture. We count 3 interstellar travelers per year at this brightness. Becomes about as often as a full moon parade in the news. Most look powdery becomes most behave like snowballs, not stones. Incoming lanes cluster along this great circle becomes they prefer a sky road that crosses here and here. This is not dumbing down. It is respect for attention and for the music of a voice that moves without strain. A quiet ethics runs through all of it. Open numbers invite help. Shared code avoids hidden traps. Honest language protects the audience from whiplash and protects the science from itself. When a value changes, we say so and show our work. When a window is missed, we say which one and why. And we add a step so the same door will be open next time. That humility is not decoration. It is the backbone that lets a field accept surprise without sliding into noise. What about the spicier edge signals, artifices, engineered sails? The policy is simple. We keep a clean baseline so that if anything truly odd appears, it stands on a flat table, not on wobbling expectations. A narrow, artificial tone in radio would be obvious against a background of noise we already understand. A push that refuses every natural cause after months of tests would be strange in a way we could describe, not just feel. Until then, we keep wonder ready and claims plain. The last fear is the most human, losing the audience to boredom while we do it right. The cure is cadence. Small, regular notes replace long silences, still unbound, no dust yet. Next radar chance on Tuesday. Faint reddening confirmed at 2 sites. No extra push detected this week. These sentences are not fireworks. They are stepping stones. They keep people close enough to feel the shape of the work without needing a glossary. When the verdict finally settles icy, rocky, mixed, or odd, the audience will already know the path we took to get there. Let the visuals match the mood. Slow star pans, a pale crescent, a soft cloud of dust in silhouette, the limb of Earth at dawn. The voice remains steady. The message remains clear. 1 traveler is a marvel. 10 are a pattern. Patterns let us speak about other suns with a straight face and a quiet heart. That is why Harvard scientists fear what 3i Atlas really island. Not because they dread the unknown, but because they dread letting a rare chance vanish into rumor or into a drawer. Fear, in this room, is a compass that points toward discipline, openness, and patience. The only tools that turn a blinking pixel into a truth strong enough to last. Imagine building muscle memory for the sky. You do not wait for a mystery to arrive. You rehearse the moves until they feel natural. That is how serious groups keep fear useful. They turn it into practice. When a candidate like 3i Atlas appears, the hands already know where to reach, which buttons to press, and who to call so the night flows instead of stalls. Rehearsal starts on screens. Analysts replay old alerts at real speed and let the room react. The software throws a faint, fast mover onto the map. Timers start. 1 person confirms the positions, another checks for thin cloud, a third pulls deep sky charts to spot lurking background galaxies. A color request goes out with exposure times listed, so a small telescope can act without extra emails. By the end of the drill, The team can say how many minutes it takes to move from spec to solid plan. Hardware rehearses too. Domes open on quiet nights, not to chase a visitor but to test cadence, how long it takes to slew, expose, download, and switch filters without wasting seconds. A camera that saves 10 seconds per cycle might buy you a full extra light curve point before dawn. A cooler detector reduces false redness in faint objects. Small wins accumulate. The sky never changes its pace, but our tools can learn to keep up. Partnerships get the same care. A single email list is not a plan. Teams maintain a living who can do what map, which observatories can see the target tonight, who has infrared, who can try radar, who sits under a possible occultation path. Phone numbers, not just addresses, sit on that sheet. When the window opens, you call a person, not a building, and you ask for a specific, measured thing. Education makes the plan breathe. New students learn to write requests that are clear and kind. Exact coordinates, suggested exposure times, sky limits, what will count as success, and by when. They also practice saying thank you in public posts when a partner delivers, because courtesy keeps networks alive between events. Behind the scenes, mentors review logs and note small frictions, file names, time zones, mislabeled filters. Those tiny fixes buy clean hours later. Data pipelines are treated like aircraft. Version numbers matter. Changes are written down. When a value shifts, you can point to the line of code and the day it changed. That discipline allows healthy argument. If two teams disagree over a faint reddening trend, they can swap exact steps, rerun each other's scripts, and learn whether the sky or the software made the difference. The goal is not to win, it is to converge. Artificial intelligence helps, but it does not lead. Models can flag odd motion, spot subtle coma growth, and predict which sites will have the cleanest skies. They can also hallucinate patterns in noise. So every AI suggestion carries a human checklist beside it. Blink the frames by eye. Compare the object's shape to nearby stars. Make sure a hot pixel did not drive the verdict. Used that way, machine help speeds honesty rather than fantasy. The public channel gets rehearsed as seriously as the telescopes. Draft updates are written in advance and kept generic until numbers arrive. Unbound path likely and no coma yet are simple sentences that calm expectations while inviting help. When a value changes, an update explains why. A longer light curve, a cleaner filter set, a new viewing angle. People do not mind change when they see the steps that caused it. Planetary defense teams sit nearby, not because 3i is expected to be dangerous, but because rare visitors are perfect drills. Tracking, energy estimates, and coordination with civil agencies all improve when tested on fast, faint targets. A harmless interstellar rock that flashes in the upper air can still teach the system to move confidently if a larger object ever appears. Infrastructure grows, piece by piece. Survey telescopes keep their wide watch. Follow-up networks stretch their coverage. Infrared missions are planned to find dark, warm movers. Radar sites maintain readiness for geometry gifts. None of these exists just for 3i, but every one makes the next traveler easier to read. The lesson is simple. Ethics stays in the loop. Positions go out quickly. Light curves are shared with enough detail to be useful. Credit spreads wide to survey techs who keep domes humming, to students who align frames at 3 a.m., to partners who drop other targets to catch a blink. Hype is kept out by habit, not by scolding. When language stays plain, good news and bad news both land softly. Even rest is part of the plan. Fatigue breeds errors that look like physics. Rotating shifts, brief handovers, and honest, "I need a break" notes keep the night sharp. A listener can feel this culture in the tone of the updates. Calm, honest, never rushed. That tone is not branding. It is the sound of a room that trusts its process more than a headline. Now connect this back to our title. Why would Harvard scientists fear what 3i Atlas really is? because they fear the costs of being unprepared for a rare, teachable night. Fear, in this room, is a good coach. It makes people rehearse, document, coordinate, and speak clearly. It keeps curiosity safe by letting ordinary tests run first. It saves the biggest words for the smallest, cleanest facts. As the stars drift on screen, slow pans. A pale limb of Earth, a soft glow along a nebula. Remember this muscle memory. The moment a faint dot jumps between frames, the room does not panic. It breathes, it moves, it asks the next right question. That is how a rumor stays a rumor, a visitor becomes a lesson, and a small object from another sun turns into a lasting piece of how we understand the space between stars. Imagine one quiet night from start to finish, the kind of night that becomes a template you can reuse 100 times. The alert lands just after sunset. A faint mover appears on the survey feed, fast, clean, a little too straight. No one says the word interstellar out loud yet. The room breathes. The first voice checks the timestamps. The second voice pulls a weather map. The third voice compares the dot to nearby stars and says, "It's real." Under the calm footage of drifting stars, the story begins to walk. The small telescopes take the opening kick. They do not chase beauty, they chase cadence, short exposures, steady rhythm, 3 basic filters. The aim is simple. Gather enough positions to tell whether the path is closed or open, enough brightness points to feel the spin, enough color to hint at surface. While those snapshots arrive, a different screen blinks with ephemerides the coordinates where the object will be an hour from now, 5 hours from now, tomorrow at dawn. The schedule starts to flow around those numbers like water around stones. By midnight, the first triangle closes. 2 sites on different continents confirm the same motion. The computer's orbit fit, shaky an hour ago, settles into an open curve. The word candidate loosens its grip. No coma shows in the stacked frames yet, but the color leans slightly redder than blue. A light curve emerges from the noise, a slow, repeating swell and fall like breathing at rest. In the control room of your mind, a pencil checks 3 boxes: path, color, rhythm, and underlines a 4th: watch for push. The next move is warmth. An infrared eye looks where the visible telescopes cannot, past glare and into heat. If the surface is powdery, warmth lingers after sunset. If it is rock, warmth drops quickly. The numbers come back small but consistent, a faint lag, a whisper of fluff. No one throws a party for a whisper. They simply write it down, because whispers add up. Just before dawn, a thin cloud tries to spoil the night. The color looks redder for 20 minutes and then returns to normal. A note goes into the log beside the frames. When you hear the explanation later, "We saw temporary reddening that matched thin cirrus," you will know the honesty came from that tiny entry made by tired hands at 4 in the morning. This is what a clean path from pixel to sentence looks like. Small truths written in time, so later confidence has a spine. The day shift takes over with coffee and second eyes. They reprocess the frames through a different pipeline and get the same orbit, the same light curve, the same soft hint of warmth. A third site, under a different sky, adds points that fill a gap in the rotation and confirm the beat. The first public note goes out, short and kind. Unbound path remains likely. No coma yet. Slight reddening appears consistent. Infrared shows a small warmth lag. A powdery surface is possible. Next steps: look for a tiny non-gravitational push as sunlight increases. Afternoon brings choreography. A radar window might open tomorrow night if the geometry holds. A handful of stations lie under a potential occultation track 2 days from now. Phone calls line up volunteers. Someone prints a single page with exposure times and success criteria, so a partner can glance and act. Another person prepares a blind analysis where the key constant that would bias the push fit is hidden until methods are locked. Caution hardens into plan. Evening returns, and with it, the visitor, a little brighter, a little closer to the Sunday. The light curve's beat remains steady. The color trends hold. and then the tiny drift appears so small it would be invisible without last night's precise positions. It grows where sunlight hits hardest, shrinks as the angle eases. The numbers do not shout, they nod. Ordinary causes step forward by themselves. If there is a coma, it is faint enough to hide in star-like seeing. Polarization checks are cued to test for hidden dust. Infrared looks again to see whether the warmth glow blooms. On social channels, the update stays calm. A small extra drift is now detected. Its pattern matches ordinary sunlight and possible faint outgassing. Deeper searches for dust and gas are underway. The words are simple, the meaning is strong. You do not need a glossary to feel what is happening. You only need the cadence of honest steps. Sometimes luck bows. The radar geometry holds. Distances and speeds come back so clean they slash orbit uncertainty and make the drift fit crisp instead of soft. The occultation shadow sweeps across two clear skies, and the blink lasts long enough to set a firm size. Now the whisper of fluff becomes a fuller voice. A body perhaps smaller than first guessed, with a surface that behaves like powder, pushed a little by heat, still showing no obvious halo in visible light. The branch of the tree, we are on icy, rocky, mixed, leans toward mixed. And then, as fast as it rose, the window narrows. The object swings past its brightest point and begins to fade. The work flips from catching to keeping, late phase checks to see whether activity cools, whether the push weakens, whether the light curve's beat stays true. The tone never changes. Curiosity never turns into rush. When the final nightly note says, drift steady, coma still faint to none, warmth lag persists, you feel closure without fanfare. Zoom out. What did one quiet night teach that another will reuse? That early positions are gold, that thin clouds can fake color and must be logged, that a small warmth lag is worth chasing because it ties fluff to push. That radar, when geometry grants it, turns maybes into lines. That occultations are worth the phone calls because a clean size unlocks everything else. That small telescopes, steady and kind, are the heartbeat of the story. Zoom out farther. What did this night add to the larger tide? One more dot on the population plot. One more example of a mixed traveler, neither a showy comet nor a silent stone, but a crust that wakes in patches and then rests. One more proof that open, shared work beats rumor every time. If later we circle a part of the sky and say, it likely came from a cold shelf in a busy neighborhood, it will be because dozens of small, honest sentences marched there in order. The camera drifts over a pale crescent and then into a velvet field of stars. The voice, still calm, returns to the title you clicked. Why do Harvard scientists fear what 3I Atlas really is? Because they fear wasting a once-in-years chance by moving out of order, by speaking louder than the numbers, by leaving a gap that could have been closed with one more call or one more frame. That fear is not a shiver, it is a guide. It keeps the lights warm, the logs neat, the plans rehearsed, and the language clear enough to carry wonder without strain. One night, one visitor, many lessons. The sky's clock keeps ticking, the public's clock keeps buzzing. Between them, this is how a small traveler from another sun becomes part of a larger, steady truth you can trust, even with your eyes closed. The room is quiet now. Most of the work is done. The numbers have settled into shapes that don't jump when you look again. What began as a rumor on a screen is now a visitor we can describe without raising our voice. It is time to answer the title with a calm truth. Why do Harvard scientists fear what 3I Atlas really is? They don't fear monsters. They fear telling the story badly. They fear missing a narrow window that won't return for years. They fear letting one fast headline outrun a careful result. In this room, fear is not panic. Fear is discipline. It taps your shoulder and says, slow down, do the steps in order, let the facts lead. The facts, at last, line up. The path is open, a one-time flyby that will not loop back around the Sunday. The brightness rises and falls with a steady heartbeat, the sign of a small body turning. A color leans a little red, the same way from site to site. Infrared checks show a faint warmth that lingers after local sunset on the surface, which is what powder does better than polished stone. And a very small extra push appears where sunlight hits hardest. The pattern you expect when gentle gas or sunlight pressure adds a gentle nudge to the path. Put together, the simplest story wins. 3i Atlas is a mixed traveler, not the loud fountain of a classic comet, not the completely silent shard of bare rock, but a crust that wakes in patches when warmed and then settles down again. It most likely came from the deep cold pantry at the edge of another star system where dust and ice sleep for ages until a giant planet or a close pass flicks a few pieces free. That is not a wish. It is a quiet sentence, built from measurements anyone can follow. Why does that sentence matter? Because each clean case turns noise into trend. First we met a riddle called Oumuamua, then we met a textbook comet called Borisov. Now a third point joins the line. With every honest visitor, the pattern grows clearer. Other suns do throw small bodies into the dark, and some wake gently rather than loudly when they pass our light. The more dots we add, the less we guess about how planets build and how debris escapes. We move from stories to statistics. The night taught the people in the room as much as it taught us about the visitor. Early positions were gold. Thin cloud could fake color, so logs had to be exact. A small warmth lag was worth chasing because it tied surface texture to the tiny push we measured. When geometry allowed, radar and stellar occultations cut uncertainty like a blade. And a chain of small telescopes, beating along through the night, turned out to be the steady heart that kept the big mirrors honest. The public path mattered too. Short, regular updates kept curiosity close and rumor far. Unbound path remains likely. No coma yet. Small drift appears. These were not hedges, they were bridges. When a number changed, we said why longer light curve, cleaner sky. New angle and trust grew instead of fraying. That trust is not decoration. It is the only way to carry wonder safely across a noisy world. People always ask about the edge cases. Would a narrow radio tone have stood out? Yes, against the static we know, it would be obvious. Would a push with no natural cause have been visible? Yes, if it refused every ordinary explanation after months of tests, it would ring like a wrong note. Neither happened here. That no is not a letdown. It is a map edge drawn in ink. It tells us our instruments were listening, our tests were working, and this time nature stayed inside the fences we understand. If a future visitor sings a stranger song, this clean baseline will help us hear it. Look forward for a moment. New surveys will watch the sky deeper and faster. More visitors will drift through some powdery, some stony, some mixed, a few odd. The kit we used, confirm, characterize, coordinate, communicate, will turn each speck into a clear sentence with less friction and more grace. One day, a small interceptor may wait in space for a sprint, and a probe will skim past a body like this and send back a close view. When that happens, quiet nights like this one will be the reason we were ready. Let's land the plane, slowly and clear. If you remember only a few lines, let them be these. Interstellar visitors are rare but real. They come once and leave quickly. Simple clues, speed, color, rhythm, warmth, tell most of the story when read in order. Tiny pushes can be measured and usually have ordinary causes. Hype is easy. Trust is earned. Fear, in a careful room, is respect for closing windows, traveling words, and numbers that outlive us. The last frame fades to a soft star field. Somewhere above the horizon, a small traveler is already growing dim, like a boat's lantern sliding into night. We didn't chase it. We didn't need to. We watched, we measured, we wrote it down, and we left a better map for the next one. That is how a rumor becomes a result, and how a result becomes part of how we understand the space between stars. Sleep now, if you like. The sky will keep its quiet watch. Another alert will come on another evening. Another room will breathe, rehearse its steps, and follow the same calm road from pixel to proof. And when a new traveler rises, we will be ready with steady hands, simple words, and a fear that points us gently toward the truth.